and its electron configuration 1s2, 2s2, 2p2. So it's got 2 electrons in a spherical 1s orbital, and that energy level is filled because it's up to helium. And then its valence electrons, there's 2 in a 2s orbital, which has the same shape but a larger radius. And it's got 2 electrons in p orbitals, and the p orbital shape is a little different than the s orbital. It has nodes above and beyond, below the plane, and there's one on the x-axis, one on the y-axis, and sticking in my gut here, there's one on the z-axis. And it doesn't really matter. By Hund's rule, there's 1 electron in 2 of these p orbitals, and then one's empty. Now that's if you have a carbon atom. And we finished up last time looking at the scenario where when carbon has 4 single bonds. And we use methane as an example, but it's true, or thought to be true. Anytime carbon has 4 single bonds, it undergoes what we call Sp3 hybridization. And if we write the orbitals again, the 1s orbital, the 1s orbital has 2 electrons of opposite spin. Again, we consider that filled, and so those electrons don't participate in the hybridization. And then we have 2 electrons in the 2s orbital, and then there's 3 p orbitals, 2px, 2py, and 2pz. And these all have the same energy, so it doesn't really matter which 2 you pick for the remaining 2 electrons. But by Hund's rule, you got to spread them out. They can't be in the same orbital, and they have to have the same spin. And so, if you have a carbon atom, which of course is very unstable, it really wants to form molecules and form covalent bonds. But if you did have a free carbon atom, it's thought of that the electrons are in these orbitals. And then we kind of finished up last time. When you look at the scenario where carbon forms 4 covalent bonds, 4 single bonds, I should say. What is thought of as happening here is all 4 of these orbitals are hybridized. And after they hybridize, you end up with the same number of orbitals that you started with. We have 1, 2, 3, 4 orbitals here. When they hybridize, they all have the same energy, and they're called Sp3 hybridized orbitals. And they're thought of as being a hybrid of the s orbital and the 3 p orbitals. And there's a total of 4 electrons here. Since they all have the same energy, it's thought of that there's 1 electron in each of these Sp3 orbitals after they hybridize. And they hybridize when carbon forms 4 single bonds. Okay? That's the scenario we looked at last time, and we're kind of reviewing it. And so when carbon has 4 single bonds, it undergoes Sp3 hybridization. In any molecule that you see a carbon with 4 single bonds, it's said to be Sp3 hybridized. And of course, there can be more than 1 in the same molecule. And the geometry of these orbitals were kind of consistent with what we talked about in valence shell electron pair repulsion theory. They point to the corners of a tetrahedron here. So here are the 4 Sp3 hybrid orbitals. They each have one electron in them. And we just use methane as an example. Again, anytime you see carbon with 4 single bonds in a molecule, it's thought of that carbon is Sp3 hybridized. But if we look at the example of methane, well, hydrogen has 1 electron in a 1s orbital, so those are the 2 that make up this covalent bond. And when it's head-on like this, it's referred to as a sigma bond. If you have another hydrogen here, a 1s orbital with 1 electron in it, you got another sigma bond. If you have a hydrogen here, 1s orbital, 1 electron, there's a third sigma bond. And then back here, if you have another hydrogen, 1s orbital, 1 electron overlapping, that's a fourth sigma bond. And so, when carbon has 4 single bonds, it forms 4 Sp3 hybrid orbitals, 4 of them, and they result in 4 sigma bonds, or head-on. Well, that's, of course, not the only way that carbon forms molecules, so that's what we're going to take a look at now. Well, what about the scenario when carbon has a double bond and 2 single bonds? Well, it hybridizes differently under that situation. And what is, according to the theory, what is thought of happening if carbon has a double bond and 2 single bonds, the s orbital and 2 of these p orbitals participate in the hybridization and form 3 Sp2 hybrid orbitals. And then you have a p orbital that didn't participate in the hybridization that's still a p orbital. Just like before, there's 1 electron in each of these, the 3 hybrid orbitals, and then there's an electron in the p orbital that didn't participate in the hybridization. And this is what's thought of as happening whenever carbon has a double bond and 2 single bonds in a molecule. And on this one, the 3 Sp2 orbitals actually are planar and triangular and flat here. And of course they have 1 electron each. And then to kind of emphasize that it's different, I suppose, I said that 1 of the p orbitals didn't participate in the hybridization, and it's above and below the plane of the Sp2 orbitals, and so we'll put it here and here. And this is a p orbital that didn't participate in the hybridization, which also has 1 electron in it. P orbitals have nodes. Okay. Well, I guess the simplest molecule I can think of where carbon has a double bond and 2 single bonds would be formaldehyde or methanol. And on this, I'm just using carbon as an example, but well, the oxygen would also actually be thought of as hybridizing, because it's got a double bond. When oxygen has a 2 single bonds, it's also sp3 hybridized. And if it's got a double bond, it's thought of as being sp2 hybridized. Well, we won't, I'm just focusing on the carbon, but we're gonna have two hydrogens here that have, again, one electron in the 1s orbital. And so you got a sigma bond here and a sigma bond here. And then it turns out the oxygen is also sp2 hybridized. I don't know exactly how to draw it so that, and with oxygen it has two non-bonded pairs, and so here are some two sp2 orbitals that are actually filled. This sp2 orbital has one electron in it that's overlapping with the sp2 orbital of carbon. And so this is head-on again, this bond. It's like a single bond. And so there's a pi bond here. But because the oxygen is also sp2 hybridized, it's got a p orbital that didn't participate in the hybridization. And this type of bond is a little different. There's one electron in this p orbital on the oxygen. Don't forget, oxygen has 6 valence electrons. It only needs to form 2 bonds. And so there's 2 sp2 orbitals that are kind of filled here. One sp2 orbital has 1 electron for a sigma bond. But then now you've got 2 p orbitals that do a sideways bonding. That's called a pi bond. And pi bonds prevent rotation of the molecule along this axis because you'd break the bond. Okay? So to summarize, and hopefully the drawings are better on the PowerPoint, but whenever you see a carbon with a double bond, 2 single bonds, it's sp2 hybridized, and it has 3 sp2 hybrid orbitals, and it has plus a p orbital that has an electron in it, and it results in 3 sigma, sorry about that, 3 sigma bonds plus 1 pi bond. And this is this overlap above and below the plane is considered 1 bond, a pi bond. Well, you can imagine it's only going to get messier here when carbon has a triple bond. And so we'll see if they have some nice slides that are easier to visualize than my drawings here. But again, I kind of made a mess here. If carbon has a double bond and 2 single bonds, it's sp2 hybridized. And there's 3 sp2 hybrid orbitals plus a p orbital, and they result in 3 sigma and 1 pi bond. If carbon has a triple bond, and I won't draw this one because it's such a mess, it ends up having 2 sp hybrid orbitals, and there's 2 p orbitals that don't participate in the hybridization, and this results in 2 sigma bonds plus 2 pi bonds. And this is also true if you have a carbon with 2 double bonds, like in carbon dioxide. When you see a carbon in a molecule, and you're not going to see a carbon in a molecule with 2 double bonds very often. I mean, carbon dioxide has it, but in organic compounds, This is a type of compound called an alene, and they're not very stable. I had to synthesize some of these in graduate school, but be that as it may, it's hybridized the same way. So it's Sp hybridized, and there's going to be 2 Sp hybrid orbitals plus 2 p orbitals that didn't participate in the hybridization. And just like with a triple bond and a single bond, you're going to have 2 single bonds and 2 sideways p orbital pi bonds. Well, my drawing's not the world's best. Let's see if maybe they have some better drawings of this hybridization. And I don't want you to think that carbon is the only element that does this. I'm just using carbon as an example. Some of you have to take organic chemistry some days and you'll see this again. But just for the record, again, let's review. If carbon has 4 single bonds, it undergoes Sp3 hybridization, and there's 4 sigma bonds. If carbon has a double bond and 2 single bonds, it undergoes Sp2 hybridization, and it results in 3 sigma bonds and 1 pi bond. If carbon has a triple bond and a single bond, it undergoes Sp hybridization, and that results in 2 sigma bonds and 2 pi bonds. And for the rare cases when carbon has 2 double bonds, it's just like a triple bond and a single bond. Carbon undergoes Sp hybridization, has 2 sigma bonds and 2 pi bonds. Oxygen actually only has 2 possibilities, doesn't it? It can have 2 single bonds or a double bond. And so it either undergoes Sp3 hybridization or Sp2 hybridization. Nitrogen can have 3 single bonds, or a double bond and a single bond, or a triple bond. And so nitrogen can undergo Sp3, Sp2, or Sp hybridization. So again, I don't want you to think that carbon's the only element that is assumed to do this. Well, again, the drawings are going to be nicer up here than mine. Here is the slide that shows the Sp3 hybridization that we were looking at carbon as an example. You start with an s orbital and 3 p orbitals. When they hybridize, if it's Sp3 hybridization, then there are 3 Sp3 orbitals. They point to the corners of a tetrahedron. And methane's an example of that. And so here you see carbon, when it has 4 single bonds, they generally point to the corners of a tetrahedron, and these orbitals involved in the bonds from carbon are Sp3 hybrid orbitals, and there's 4 of them. Well, here is nitrogen. If nitrogen, like in ammonia, has 3 single bonds, it's also Sp3 hybridized, but one of the orbitals has 2 electrons in it, and the others only have 1, and so they form covalent bonds to hydrogens. Now, I don't know, now they're kind of going to the very beginning of all this and looking at hybridization of some of the simplest main group elements. Beryllium doesn't obey the octet rule, and they can form 2 covalent bonds and no lone pairs. And so in compounds, beryllium only has 4 electrons around it. And this particular molecule is Sp hybridized. And beryllium's 2 valence electrons are in Sp hybrid orbitals, and there are no electrons in other orbitals, although to a chemist, the orbitals are still available, even if there's not electrons in them. And so and when it's Sp hybridized, there's an empty p orbital above and below, and another empty p p orbital sticking out, hitting me in the nose and back into the plane, but there's no electrons in them. Here, boron, when it forms compounds like boron trifluoride, it doesn't satisfy the octet rule, but it does undergo Sp2 hybridization, and when it does, there's one electron in 3 Sp2 orbitals, and you have a triangular structure here. And then these, again, anytime it's head-on like this, the bond doesn't involve p orbitals above and below the plane. These are sigma bonds. They're just direct head-on type covalent bonds. So boron doesn't satisfy the octet rule, but it does undergo Sp2 hybridization in making molecules. And so here it's kind of showing you d orbitals can also participate in hybridization. Of course, with carbon, we didn't look at an example of that. Carbon doesn't have any electrons in d orbitals. But here it's kind of showing you the hybridization involved in forming a few of these molecules. And the electrons, you include the lone pairs and the bonding electrons as to determine the hybridization. Here's a slide that's hard to see, but it's showing you examples of these things. When you have Sp hybridization, but there's only 2 hybrid orbitals, like in the case of beryllium, it's linear. Boron, Sp2 hybridized, it has 3 Sp2 orbitals and no lone pairs. It's trigonal planar. We looked at the example of methane. When it's Sp3 hybridized, there's 4 Sp3 hybrid orbitals. And this is also true of the polyatomic cation ammonium. That's not the same thing as ammonia. Nitrogen has bonds to 4 hydrogens, and it has a positive charge, but it also is, this is an example of Sp3 hybridization of a polyatomic ion, the nitrogen in the polyatomic ion. And then here, phosphorus pentachloride, Sp3D hybridization, sulfur hexafluoride, Sp3D2. And of course, this theory has to be quasi-consistent with the valence shell electron pair repulsion theory we talked about. Now here, took a look at this, but this is much nicer drawing than mine. When a carbon has a double bond and 2 single bonds, the carbon is thought of as being Sp2 hybridized. Here are the valence electrons. You don't worry about the filled shells at all. Carbon has a total of 4 valence electrons, 2 in the 2s orbital, and then 2 of them in separate 2p orbitals. When we hybridize, we ended up with the s orbital and 2 of these p orbitals hybridize and form the sp2 orbitals. And then there's 1 p orbital that's circled here that did not participate in the hybridization. And these 3 hybrid orbitals in the p orbital all have 1 electron. And here it kind of shows you the geometry of an sp2 hybridized atom, including carbon. Carbon here has 3 green orbitals that are sp2 hybrid orbitals that point to the corners of a triangle. I tried to draw that. And then here in gray is a p orbital that did not participate in the hybridization. Well, if you have a compound like ethylene, and they're using ethylene as an example of sp2 hybridized carbon, you actually have 2 carbons that are both sp2 hybridized. This carbon has a double bond, 2 single bonds, so it's sp2. This carbon has a double bond and 2 single bonds. It's also sp2. And so here is an example of sp2 hybridization involving 2 carbons. And as we mentioned before, if you look at just one carbon, there's 3 sp2 orbitals that are going to result in sigma bonds, and this carbon has the same 3 hybridized orbitals as well. And then they both have a p orbital above and below the plane, and it's a sideways overlap. That's why they call this type of bond a pi bond. It's a different type of bond than a sigma bond, which is direct overlap. Okay, so this carbon, if it's sp2 hybridized, has 3 sigma bonds and 1 pi bond. Don't forget, above and below, this is 1 bond. P orbitals have nodes. And then this carbon's also sp2 hybridized, so it has 3 sigma bonds and again 1 pi bond. And they spell it out here, what's referred to as a sigma bond, electron density between 2 atoms. Pi bond, electron density above and below the plane of the nuclei of the bonding atoms. And in the case of a carbon-carbon double bond, because of these pi bonds, these bonds don't rotate, because you would be breaking the pi bond, wouldn't you? That hot dog up there is actually a bond. If you tried to rotate the carbon-carbon double bond, you'd break the pi bond. So and this is something that's experimentally verified, carbon-carbon double bonds don't rotate the way carbon-carbon single bonds can. Generally speaking, if you're looking at a specific bond involving carbon or oxygen or nitrogen, if you're looking at a single bond, it's going to be a sigma bond. If you look at a double bond, it's going to consist of 1 sigma bond and 1 pi bond. If you look at a triple bond, it's going to consist of 1 head-on sigma bond and 2 pi bonds. Here is kind of a view of the molecule from the side, so you can kind of see the pi bond being above and below the plane. Both of these carbons are sp2 hybridized, and so both of them have a p orbital above and below the plane that ultimately give rise to the pi bond. Pi bonds are generally thought of as being formed by this overlap of p orbitals. Now for sp hybridization, and I didn't even attempt this one on the board, but carbon, again, it has a total of 4 valence electrons. If the s orbital here and one of these p orbitals hybridize, now you end up with 2 sp orbitals, and then the other 2 p orbitals don't participate in the hybridization, so they're still p orbitals. And as we said before, if you see a carbon in a molecule with a triple bond and a single bond, or if you see a carbon with 2 double bonds, then it's sp hybridized. And here they're using the example of acetylene or methane. And acetylene or ethine has a carbon-carbon triple bond. And so both of these carbons, this carbon has a triple bond, a single bond, it's sp hybridized. This carbon has a triple bond and a single bond, it's also sp hybridized. Whenever you see a carbon with a triple bond and a single bond, it's sp hybridized. And whenever you see an sp hybridized carbon, you know there's going to be 2 sigma bonds and 2 pi bonds. And here you can kind of see, if we look at just one of these 2 carbons, the sp hybrid orbitals are linear and give rise to 2 sigma bonds, one between this carbon and this hydrogen, and another sigma bond between this carbon and this carbon. And then above and below the plane, in 2 different orientations, are p orbitals that didn't participate in the hybridization. So you're going to end up with 2 pi bonds. Don't forget they have nodes. And so one is above and below the plane here, and one is on this side and the other side. Again, it has nodes too. These 4 Oscar Mayer wieners here, these are 2. When you see these 4 pi's, they really correspond to 2 pi bonds that are above and below the plane. Okay? Okay, well, we already looked at formaldehyde, but again, this carbon in formaldehyde, what can you tell me about it? How is it hybridized?
Sp2.
It's Sp2 hybridized because it's got a double bond and 2 single bonds, so it's Sp2 hybridized. And so how many single bonds will it have?
2.
No, that's Sp. How many sigma bonds?
Sigma 3.
3. And then how many pi bonds?
1.
1. Okay, good. Now this oxygen is also Sp2 hybridized, but it only forms 2 bonds. Since it's Sp2, it's going to have 2 pairs of electrons in Sp2 orbitals, and then it's going to have 1 sigma bond and 1 pi bond. And here it shows you the sigma and pi bonds. The carbon has 1, 2, 3 sigma bonds and 1 pi bond. The oxygen has 2 pairs of electrons in Sp2 orbitals. The oxygen has 1 sigma bond and 1 pi bond. Don't forget, oxygen only forms 2 bonds. Carbon forms 4. Alright, now that's the kind of a whirlwind introduction, except if you kind of follow the rules. Let's say it again. If you see a carbon with 4 single bonds, it's Sp3 hybridized, and it has 4 sigma bonds. If you see a carbon in a molecule with a double bond and 2 single bonds, it's Sp2 hybridized. It's going to have 3 sigma bonds and 1 pi bond. If you see a carbon in a molecule that has a triple bond and a single bond, it's Sp hybridized. It's going to have 2 sigma bonds and 2 pi bonds. Okay? And again, if you take organic chemistry, you'll see it again. Okay? Any question about the valence bond theory? Easy for me to say. Any question on that valence bond stuff? Okay, I'm just going to talk a few minutes about molecular orbital theory, but we're going to I think we have time to cover it next class, because it's a third theory and it's different than the other 2. These different theories, they overlap in some ways, and then in others, they explain exceptions and things. And just to remind myself here, we said we're going to wait until Yeah, we got quite a bit of time. We're gonna wait until, is it May the 1st to take the 5th exam, right?
Yes.
Okay, so we have both Tuesday and Thursday of next week. Tuesday to look at molecular orbital theory, and Thursday to review for the 5th exam. And don't forget about lab notebooks and sampling homework and all that good stuff. And also for the lab, don't forget about the lab report. Well, molecular orbital theory, we're going to talk about it in detail next time. But based on valence shell electron pair repulsion theory, I suppose. No, not really. Based on valence bond theory and Lewis dot structures, which really is not much of a theory per se, but and if you were taking an introductory chemistry class, and I would just tell you that oxygen forms a double bond with itself. End of story. But there's experiments that have shown that this can't actually be the actual Lewis dot structure for oxygen gas, and the reason is its magnetic properties. If in fact oxygen, when it bonded to itself, if it had a sigma bond and a pi bond, and it had 2 pairs of electrons on each oxygen that were in Sp2 orbitals, the spin states of the electrons would cancel each other's magnetic fields out, and they wouldn't be expected to have magnetic properties. But here you see liquid oxygen, and that's going to be cold. Don't put your finger in it. It's actually attracted to the poles of a magnet because of the magnetic properties of this molecule. And this is because oxygen is diamagnetic. There must be some basis for this in an electron that's not part of a pair in an orbital. And so this is the fact that that oxygen is paramagnetic instead of diamagnetic. It actually has magnetic properties. Suggests to chemists that there must be something else going on. And that is just one example of the basis of what we call molecular orbital theory. And we're not going to go in too much detail today, but when you're considering molecular orbital theory, it's best, first of all, to start off with 2 atoms of the same element. And of course, hydrogen is the simplest element. And we know in advance that hydrogen, when we have the element hydrogen, it exists in clusters of 2, and it bonds to itself. We also know the next element, helium, on the periodic table, doesn't do that. In other words, if you bring 2 helium atoms together, there's no energetic benefit in forming a bond. Bonds form because molecules are more stable than free atoms. Well, we're just looking at this one example today, and we're going to go into this in more detail next time. But when you bring 2 atoms together, and the first pairs of atoms we're going to be talking about are of the same element. And you know that the electron configuration of hydrogen is 1s1. It has 1 electron in a 1s orbital. And if we're bringing together 2 hydrogen atoms, we have to have a second hydrogen over here that has 1 electron in the 1s orbital. And what we're doing is we're bringing these atomic orbitals of these 2 atoms together, and they're resulting in 2 molecular orbitals. And when these molecular orbitals are formed, again, they're of the 2 types that we already talked about, sigma, and pi. Any electrons in s orbitals are thought of as forming sigma bonds. And you can kind of see molecular orbital theory sort of borrowing from the concept of valence bond theory. When these two 1s orbitals from the two hydrogen atoms were bringing together, trying to see if they form a bond, well, one of the molecular orbitals has lower energy than the atomic orbitals do, and we call that a bonding orbital. And then the other orbital that's formed is actually an anti-bonding orbital, and it has to do with their wave functions, but essentially in a bonding orbital, it's thought of that the constructive interference of the wave of the electron are complementary each other. And in the anti-bonding orbital, and we use an asterisk to represent an anti-bonding orbital, and it's destructive interference. They're sort of out of phase and canceling each other out. So we start off with two atomic orbitals, one from one hydrogen and one from the other. And we made two molecular orbitals, and notice that it's sigma 1s and sigma 1s star. S orbitals typically give rise to sigma bonds. Sigma 1s, it would be a bonding orbital that is generated by 1s atomic orbitals. Sigma star 1s would be an antibonding sigma orbital that's generated by 1s bonding orbitals. And so that's the designation or nomenclature in naming these things. Well, notice that just like the Aufbau principle, when we were talking about electron configurations, we filled orbitals from the lowest energy and we worked our way up. And here we have one electron from one hydrogen atom and another electron from the second hydrogen atom. And so we put both of them with opposite spin in the lowest energy orbital. And now you see when we bring two hydrogen atoms together, we have two electrons in a bonding orbital, and we don't have any electrons at all in the anti-bonding orbital. Well, it's got to be the world's simplest equation, and here it's talking about constructive and destructive interference here. Anyway, I'm trying to find you the world's simplest equation. This is one your kids can play with. The equation's bond order. And the bond order is 1/2 the quantity, the number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding orbitals. And if the bond order is greater than 0, the bond forms. Well, that was easy, right? So let's go back to our hydrogen. And we're going to look at other elements, but today all we're looking at is hydrogen. Well, we have 1/2 times the quantity. There's 2 electrons in the bonding orbital, none in the anti-bonding orbital. When I was in school, 2 minus 0 was 2, and then times 1/2 is 1. The bond order is 1, it's greater than 0, and a bond forms. Simple. Okay? Now you can guess if you bring two, I'm not going to do it today, but we'll do it next time. When you bring 2 helium atoms together, well, the bond order ends up being 0. There's no advantage in forming a bond, and so a bond's not formed. Okay? We already know from what we've learned this semester that hydrogen does bond to itself and helium doesn't. It's a noble gas. Okay? And the bond order is kind of reinforces that. So this is where we're going to pick up next time. And when we have the next exam, I'm going to have some handouts and slides and things on there about bond orders. But some students get confused. Don't get confused. On the left, whatever atom this is, you're just going to put in the electron configuration for it. whatever atoms over here, you put in the electron configuration for that. And then when you bring them together, the total number of electrons you have on the left and the right are reassigned into these molecular orbitals. You have one here and one here is 2, and so we had to put 2 here. We don't have any left, and so we didn't put any at all in the antibonding orbital. But essentially, that's what's being done here. 2 atoms are bringing their valence electrons together, so to speak, and creating molecular orbitals out of their atomic orbitals. And then, just like with electron configuration, we fill the molecular orbitals from the lowest energy and we work our way up. And as you can probably imagine, we really don't need to worry about filled shells. The bond order of the filled shell is going to be 0, but that's not what we're concerned about. It's the electrons above the filled shell, and what's the bond order of those. Alrighty, well, I've got to, I gotta get you guys set up in the lab. I try to do it before class, but